The paper of the day is Calvin, Fast Distributed Transactions for Partitioned Database Systems. Calvin is all about pre-ordering transactions in logs in batches and then deterministically executing this log in the same order in replicas. The key technical feature that allows Calvin scalability in the face of distributed transactions is a deterministic ordering and logging mechanism that enables the elimination of distributed commit protocols. Since the schedulers get a good look of which transactions are coming next in this log, they can perform optimizations by pulling some independent transactions locally and executing them in parallel in worker partitions with no ill effect. Kelvin achieves good performance thanks to batching and optimizations pulled by the schedulers by looking ahead to transactions in the log. The downsides are the loss of conversational transactions execution as in SQL and high latency due to this batch processing. Here's a cool diagram of Calvin's architecture. As you can see, there's a client applications, then we have like replica A, replica B, and each of these replicas, they consist of the storage layer, then we have scheduler, and then we have sequencer. So the schedulers, they are responsible for low isolation reads and single partition snapshot reads, and transaction and distributed snapshot reads also happen through sequencers. And then we have transaction execution threads, and then we have the storage layer. In Calvin, there is a master replica which exports sequenced log to the other replicas. The other replicas then execute the log in the same deterministic way as the master replica, and this makes a good demonstration of state machine replication or SMR in action. The sequencing layer intercepts transactional inputs and places them into a global transactional input sequence. The sequence will be the order of the transactions to which all replicas will ensure serial equivalence during their execution. The scheduling layer orchestrates transaction execution using a deterministic locking scheme to guarantee equivalence to the serial order specified by the sequencing layer, while allowing transactions to be executed concurrently by a pool of transaction execution threads. In terms of evaluation, the paper evaluates Calvin using a TPCC benchmark as well as a micro benchmark they created. Throughput results for Calvin are very good, especially when most transactions are partitioned local transactions. But as mentioned before, the downsides are the loss of conversational transaction execution as in SQL and high latency due to this batch-based processing. Looking at the contributions, there are three key contributions of the paper. The design of a transaction scheduling and data replication layer that transforms a non-transactional storage system into a linearly scalable shared nothing database system that provides high availability, strong consistency, and full asset transactions. A practical implementation of a deterministic concurrency protocol that is more scalable than previous approaches and does not introduce a potential single point of failure. A data prefetching mechanism that leverages the planning phase performed prior to transaction execution to allow transactions to operate on disk resident data without extending transactions' contention footprints for the full duration of disk lookups. And there's a fourth contribution, which is a fast checkpoint scheme. Together with Calvin deterministic guarantee, completely removes the need for physical redo logging and its associated overhead.